All right, in the last couple videos, I did nozzles. For those, those are pretty straightforward. The equations are very nice, kind of just plug and chug. There's no like derivatives, there's no integrals, there's no differential equations, there's none of that. This video, I'm gonna go over shockwaves and expansion fans. And they also have straight up very simple equations that you just plug and chug, and that's it. So, first of all, what is a shockwave? So, a shockwave, so let's say you've got an airplane, and I'm gonna draw an airplane as a triangle. It's moving that way. So, let me write it. This is moving that way. The air is relatively moving that way. So let's say the air is moving at Mach 1, or a Mach number, and I'm gonna call that Mach 1. An oblique shockwave, a normal shockwave would look like that. It would be normal to the velocity. There's a right angle right there, so it's normal. Oblique shockwave will look like that. So there's an angle here, and I'm gonna call this one theta, and there's an angle here, and I'm gonna call this one beta. And same down here, theta and beta. So we saw that with a normal shockwave, what does it do? It decreases the Mach number. So I'm gonna write it up here. You know, I'm gonna write all of it up here. So you have Mach number, pressure, temperature. And you have Mach after, and pressure after, and temperature after. 1, 1, 1, 2, 2, 2. So a normal shockwave would decrease the Mach number, increase the pressure, increase the temperature. Exact same thing is true with oblique shocks, but they don't decrease the Mach number as much, and they don't increase the pressure as much, and they don't increase the temperature as much. They do all of them, but just to a less extent. Okay. So I mentioned the equations for this were like very similar to nozzle and to the normal shockwave equations. And they are okay. Before I write them down, we can do some other math. So, okay. So we know theta because that is in the design. When you design an airplane or a rocket, you know theta. You also know the Mach number because let's assume you can measure it some way. So based on those two things, if you know theta and you know the Mach number, you can use this table. So if you know theta and you know Mach number, you can get beta. You can get this beta angle. So how do you do that? You use this table. I don't know what it's called, but I just freaking have it in my notes. So let's assume, what should we assume? Let's assume the angle is 20 degrees. I'll write it here. Angle, I'm gonna write it on the side actually. Let's assume angle is 20 degrees. Let's assume you're at Mach 3. All right, so the way this would work is you follow this line. I'm gonna change the color actually. red, Mach 3, follow this line, I detached. And then you draw a line over, and you get, I don't know, let's say you get, what would that be, like 37? 37 degrees. So we got 20 and 3 equals 37. So that means, and it makes sense because you want the beta to be more than theta. You want beta to be more than theta. Okay, now you notice the line also goes up here. And no cap, I forgot why. But you never really use it, I don't think, for anything that's like important. But okay, so there's one more concept. So let's say that we are at 30. That's a 3, but it's supposed to be a 30. Is it? There's no way. There might be like a 32 or something. All right, let's say we're still at 20. So we're still at 20. But now we are at Mach 1, let's do 1.5 because it's a nice number. 1.5. Draw this line. And you realize this line never intersects with it. So like, what the heck? What does that even mean? That means, go back to black here. That means that, let me just draw another triangle. Assume they're unrelated. I'm just using the same center line. Theta. That means that you have a detached shock wave. So it'll look like that. It's detached from the nose of the rocket. There's a gap there. There is a gap. I'm trying to draw it all the ways possible. Versus over here, there's no gap. It starts right there. Okay, any other conceptual things? Well, I guess now we should write out the equations before I talk about that. Okay, so what are the equations? The equations are all right, well, okay. Yeah, okay. All right, there you go. So if you know M1, you know K, you know theta, you know beta, you can get M2. Yeah, so it's well, there's a lot of stuff in the equation, but like it's pretty straightforward. Yeah. Is there anything else I wanted to say on that right now? I don't think so. We can move on to the next one. So pressure. And again, M1 and M2. So 1 is before the oblique shock, and 2 is afterwards. So 1 is like out here, and 2 is inside of here, between the oblique shock and the surface. All right, pressure. That's it for beta, or for pressure. And then temperature. Oh, dang, this one's massive. All right, I'll try to write it here. I bet I'm gonna miss one tiny thing in one of these equations and someone's gonna get really mad. They're gonna be like, what? It's not working. Why isn't it working? I just asked ChatGPT at that point. All right, so far I think it looks good. Stuff on the bottom. Okay, there you go. Those are the 3 equations, and they're very similar to the old ones, especially the normal shock ones, but they're just slightly different. Okay, so a couple interesting things to note. Yeah, I guess we could just go over this plot. So this is basically saying if you increase the Mach number, the beta angle decreases, but this stays the same. And we could actually see if this is what we get. So if you're at Mach, is 20 on here? Oh, it is. It's right there. Let's not do it though. Let's do Mach 2 and 20 degree theta. Mach 2, 20 degree. That will go up to this line. Go like 52 or something. 53. Yeah, okay. So that makes sense. But it's saying as the Mach number increases, beta angle decreases. I guess we could have gone over this earlier, but yeah, that's fine. That's kind of all you need to know here. Next is expansion fans, which they are whenever there's kind of a negative angle change. Like here, there's a positive angle change, and here there's a negative angle change. Does that make sense? Hopefully that makes sense. So, what do you do? Okay, so let me draw it out. Let me draw out what they have. So you're gonna have them right there. I'll draw it on the bottom because the top is pretty crowded right now. So on this side, you have M1, P1, T1. And on this side, you have M2, P2, T2. And the interesting thing is it speeds up as it goes across. Yeah, so Mach 1 is less than Mach 2. So it's the opposite of an oblique shock. Because oblique shock, it would slow down as it passes through. But for an expansion fan, it speeds up as it passes through. And that means that the pressure and the temperature are the opposite. Cool. So, what's step 1? All right, step 1 is we use the table. So we know the incoming Mach number. We know Mach 1. And we know, dang it, maybe I shouldn't write this close. I'll write down here. We know Mach 1, and we know theta. We know, I'll draw it on my picture. So this is a straight line. We know theta. And we know the incoming Mach. And we're trying to find, should I draw it that way? I'm gonna just draw it straight. We know the incoming Mach, we're trying to find the outgoing Mach. So how do we do that? So let's say our incoming Mach is 3. So let's say our incoming Mach is 3 and our theta is 5, let's say 10 degrees. So we'd find 3. So this is Mach number and W. I'll get to it. So Mach number, where is 3? 2.5, 3, right here. I'm gonna make it red. Okay, so what do we do with that? So we use M1 to find W1. These are W's, or omegas, or whatever. I call it W. To find W1, and then we do W1 plus theta, and then, oh, that equals W2. And then we use W2 to find M2. So let's do that. So we got 49.76 as W1. So M1 is 3. W1, 49.76. Is that it? Yeah, 49.76. And then we do W1 plus theta. So 49.76 plus 10 equals 59.76. And then we find 59.76. 59, that's close enough. 59.78. So we get 3.58 as our Mach 2. So you can see our Mach number increased. It went from 3 to 3.58. Cool. So that's our Mach 2. Okay, and then what equations do we have? We have temperature and pressure. So let's do temperature. that it? That's it. It looks a little ugly, but that's okay. Okay, and then pressure. It's literally the exact same equation, except it's to the power of k minus 1. There you go. Those are those two equations. And I think that's about it. So like, I think for me on like a test or a homework or something, we were given literally this shape, like this exact, basically this exact problem. We were given this, we were given the angles, and we were asked to find M2 and M3, M4. I forgot how I did this one. I forgot if we even did that one. Oh, it should be the same thing, because the way I said it earlier, this is a positive angle. This is a negative angle, technically. Even though when I say that, you still always add it. You still always add it, and you get a bigger number. Don't put in -10. And this would technically be a positive angle. And positive angles have oblique shocks, and negative angles have expansion fans. So yeah, I think that is literally it. Let me box some of this stuff. Cool beans. Yeah, so again, for this one, for, what's this even called? Oblique shockwaves, you needed to calculate M2, but you could find beta. You could find beta with the chart. Here, you can find M2 with the chart. You don't calculate it, you just find it with the chart. And all you need to do is calculate T2 and P2. And again, state 1 is on the left side of whatever you're looking at, and state 2 is on the right side of whatever you're looking at. Let me draw that. So that's like over here. And these are like over here. Cool beans. And again, this is moving that way with a Mach number, and air is moving this way with the same Mach number, but like opposite direction. I think that's literally it. Cool beans. All right, I wanted to mention one more thing. Instead of using these tables, there are equations, but they really suck. Like really suck. So I'm gonna draw them over here so no one ever has to look at them. So for this one, we knew theta, we knew Mach number, trying to get beta. Unfortunately, the equation looks like this. That really sucks. Unfortunately, it's even worse. You're trying to solve for beta. It's not like a beta equals something. It's something equals beta. And it freaking sucks. Like, it's a terrible equation. And I think if they tried to solve for beta, it would look even worse. So I don't know, just use Desmos or something. Or just use the freaking tables. I would use the tables. Likewise, if we know that the Mach number is 3, and instead of using a table to get the 49.76, we could use an equation. And that equation is I'm not calling this Mach 1 or Mach 2 because it's just whatever Mach you have, because you're going to use it to find W1 and you're going to use it to solve backwards. When you have W2, you're going to use it to solve backwards to get the Mach number. So it's not Mach 1 or Mach 2, it's just both of them kind of. This actually goes over those. And then that closes, and that closes. Then there's more. Square root. I don't need it to be that big. There you go. Yeah, it sucks. They both really suck. So I'd highly recommend, as someone who really likes using equations whenever I can, just don't do it here. Just use the tables. And with this one, it's nice because you can see when it becomes detached, and it's all super visual, and it's great. And by the way, with this equation, you're going to get 2 solutions. That's why it's a parabola like that. But yeah. That's it.